Hello guys, and welcome back to Teachita. In this video we're going to analyze the tensile test in Abaqus. We're going to start with part module. Click on part, click on manager, click on create. We have a 3D deformable solid part. We're going to use revolution to create this part. Let's close this window. All the sizes that we're going to have in this sketch are per meters. This will help us in assembly and material modules when we are defining other constants. We're going to start with a line of size 0.09. We will continue with another line of size 0.01 and so on and so forth. As you can see here, we're going to create an arc as well. Now we're going to mirror this sketch around this line at the bottom. First, we're going to change this line into a construction line. I'm going to click on edits, click on transform, click on mirror. The type of mirroring is going to be copy. First, we need to define the mirror line, and now we're going to select the rest of the sketch to mirror around this line. You need to hold down the shift key to select multiple lines. Click done. Since we want to use revolution around y-axis, we need to translate this whole sketch onto y-axis. The goal is to revolute this sketch around y-axis to reach the final shape as required. Let's go under edit, click transform, and then click translate. This time it's move type. Now we're going to select everything. Click done. We'll select the start point, which is this corner right here, and then the end point would be somewhere on y-axis. Click done. Now we're going to revolute over y-axis by 360 degrees to get the desired model. Now we're going to move on to property module. We're going to use Johnson-Cook model for ductile metals. Click on material, give it a name as Al. Under general, click density, provide the density for aluminum, which is 2700. We're going to move on to mechanical. Under elasticity, click elastic, provide Young modulus and Poisson ratio as always. Now we're going to go under mechanical, click plasticity and click on plastic, and we're going to change the hardening to Johnson-Cook, and we will provide the constants as shown here. We're going to define damage for ductile metals. Under mechanical, we're going to use Johnson-Cook damage, and we will provide the constants as shown here. We're gonna go under sub options and click on damage evolution, change the type to energy, and then we will provide a fracture energy of 42,200. Click on OK and then click on OK again. Now we click on section. We have a solid homogeneous material. Click on continue and then click OK. And then we will assign this material to the part. Click OK. Let's move on to assembly module. Click on instance. Click on create. Ensure type is independent. And then click on OK. To make this analysis simpler, we're going to define a reference point above the part and assign the reference point to the part so that any properties that we assign to the reference point will be assigned to the part as well. To do so, we're going to go under Tools, click on Datum, select midway between 2 points, and we will select the top 2 points on the top surface. Now we're going to use the offset from point to create another point, and we will give it 10 centimeters above part. In reality, this would be the point that the part is attached to the equipment during the tensile test. Now let's go under Tools, click on Reference Point, and click on this point that we defined previously. Let's go under Tools, click on Set, click on Create. We're going to give it a name as RF, and then click Continue. We're going to select the reference point and then click Done. This means the RF set is representing the reference point. Let's move on to Step module. Click on Step, click on Manager, click on Create. We have a dynamic explicit problem. Click Continue. Time period is 1 second. We're going to use mass scaling. Click on Create. We're going to use a scale to target time increment of 4e-5. Click on OK and then click on OK again and then close. Let's go on to Output. Click on Field Output Requests and click on Manager and then click on Edits, and under State we're going to select the status. This will ensure to show us if any element reaches plastic region. Click on OK and then close. Now click on Output, click on History Output Requests, click on Manager, click on Edit. We're going to change the domain to Set, which we define as RF. Now we're going to ask the software for the RF set to provide the displacement in U2 axis, which is Y-axis. We also need to check the reaction forces for RF2. Click OK and then close. Since we are going to attach this reference point to the part, these displacements and reaction forces that are going to be calculated for RF1 are in fact displacements and reaction forces for the end of this part. We're going to move on to Interaction module. Click on Constraint, click on Manager, click on Create. We're going to have a coupling constraint. Click Continue. We're going to select the reference point, click Done, click on Surface, and select the top portion surface. Click Done and then click OK and close. Now let's move on to Load module. Let's define boundary conditions. Click on BC, click on Create. As we know in a tensile test, the bottom of the piece is fixed and has no displacement. Therefore, in initial step, the displacement rotation at the base is going to be fully constrained and fixed. Click Done and select all degrees of freedom. Click OK. Now for the top portion, click BC, click Manager, click Create. For the top portion, we can only have displacement in Y-axis. We're going to select the RF, click Done. We're going to select all degrees of freedom except U2. It is important to note that since we coupled the reference point to the top surface portion, we only need to assign these boundary conditions to the reference point. Click OK. Now for BC2 propagated, click on Edit. We're going to say how much U2 is going to be displaced using this equipment. As an assumption, let's say this piece is going to move 10 centimeters. At this point, since this is an explicit analysis, the software is telling us we need to define an amplitude. Click Dismiss and click this icon, which is Create Amplitude. Click on Tabular. We're going to say at time 0, I have an amplitude of 0, and at 0.1 second, we have an amplitude of 0.1, and so on and so forth. Provide a linear distribution up to 1 second that we had set up before as the time period. Let's close this window and then change amplitude to amp1 and click OK. Now we're going to move to Mesh module. Let's click on Mesh, click on Controls, and we will select an element shape of TET. Click OK. Our element has changed color to a pinkish color, which means there are no further errors. Click on Seed, click on Instance, and then provide a mesh size of 0.0055, which is the default size. Click OK and then assign the mesh to the part and click Yes. We're going to move on to the job module. Let's give it a name as Tensile Test. Click Continue, click OK, and then Submit. This error is because the name of this job is the same as the name that we used before. So we're gonna just change it a little bit and then click Submit again. Now we have to wait for Abaqus to solve this problem. You can click on Monitor and see the process of solving this analysis. Let's click on Results. We can see the stress throughout the part. The stress in the middle section is extremely high, as you can see here. We can click on Animation and see what happens during the test. We can also change the variable to displacement or U, and then we can see the displacement in y-axis, which is U2. We can also see the strains here. Thank you so much guys for watching this video. Please subscribe to our channel and hit the like button. If you have any questions, leave a comment down below and we'll get back to you as soon as possible.